Hello, it's James here. It's part 3 of the Open Dog project, which is going to be a significantly sized robot dog. It's about 900mm long, about 600mm tall, and is made from metal. So it's a totally open source project, and I'm going to be publishing the CAD and code as we go. We've already done 2 parts looking at the overall design and prototyping one leg. And that looks like this. This is actually made of extrusion, and we've got a big brushless motor here which drives a ball screw, so we're using the ODrive Robotics brushless motor driver. This is basically prototyped. We've got some 3D printed parts here. Eventually we'll be CNCing some parts on the CNC machine to replace those with aluminium. This is really just a test to see if the code works we've already written, and that can control the length. So it works back the trigonometry. We've got an inverse kinematic model, and at the moment we can put in the leg length and it works out correctly the actuator length from that joint to give us the right angle at what will be the knee essentially. But that was a bit jittery last time due to some problems with the joystick, but just generally the PID loop is tightened up quite a lot, so this will actually hit the spot really fast. So today, first of all, we're going to look at some motion smoothing, then we're going to make some more prototype parts. So I've written a filter which is basically going to smooth out all that data, and it's pretty simple actually. All it does is makes a filtered value, it bookmarks that, so it bookmarks the previous filtered value, and this is the actual filter, which basically the filtered value is the original value plus the filtered previous value multiplied by a filter constant essentially. In this case it's about 15, and we can change that for a different response, and divides that by the filter plus 1. And I actually stole this code directly from Matt Denton, who you may remember from the giant Lego that's been in my channel, and his channel, the bulldozer and the go-kart and all those things. And Matt's the guy who built the Mantis robot, the giant hydraulic walking machine that we took out to Maker Faire Hanover. So have a look at part 5 of his Mantis hacks, where he explains exactly this, and I've just basically lifted that code. I haven't put it in a function. Eventually all of these things will be put in functions. For now it's just written out longhand, and that should smooth out the value. So if we have a look at the serial monitor here, we can see the value. So the one on the left is my demand position for my leg length. The middle one is the trigonometry that works out the actuator length, and you can see that jittering because this joystick's slightly loose and it's a bit rubbish. And the one on the right here is the smooth value, so you'll see if I make an extreme move, that takes some time to catch up. And it's easier to see what's happening if we have a look at the serial plotter here. So here's the actual value. The top value is the demand position. We can see there's quite a lot of jitter there just because that joystick's loose in the middle. And we've got the 2 bottom values. The red one is our trigonometry, raw trigonometry, working out that actuator length. And the green one is now our nice smooth value. So look how lovely and smooth that green line is. And we can change that filter value to a different constant. Higher value means more smoothing, and that gives us a much better response. So if we just let that settle and wiggle the joystick there, you can see the green line does move a bit, but it's nothing like the jitter we got last time. So now we've hooked our Arduino back up to the ODrive. We're actually using software serial on the Mega, so I was a bit worried they wouldn't be able to write quick enough because software serial's got quite a big overhead on the processor, but it looks like it's fine. And I was worried that was part of the jitter problem, but it isn't. So now if I turn my knob, we can see we've got that lovely smooth response there. Let's just move the camera that way a bit more so you can see the ends. So it's still quite responsive. But that's actually got that lovely sort of thing where it smooths out and decelerates towards the end. And obviously that little bit of joystick jitter, you can still see the motor turning, but it's nothing like as horrible as it was before. So the other question I got last time was about how strong this is, and you know, because the weight of all these ball screws and motors is going to add up, it's going to be over 30 kilograms. Obviously it's only got plastic parts at the moment, but I'm going to do a bit of a strength test. I'm going to try really carefully not to break the plastic parts. But if I just sort of hold this down, and it's really strong. I mean, I can't hold that back basically. I'm pretty happy with that. Of course, at the moment, I'm only running it on 24 volts with a 24 volt version of the ODrive, and I could go up to 48 volts. I might buy the 48 volt versions of the ODrives and run it on 36 volts, so it'd be even stronger. And I'm currently limited to 30 amps in firmware, and that could go right up to 70. So it should be more than strong and more than agile enough. The other thing I quickly need to say is about the knob on the remote. At the moment, I'm turning that knob and it's controlling the leg length. In fact, that will just be a small part of the kinematic model, so I won't directly be driving leg length from that knob. I'll be driving the actual height of the robot off the ground, And that leg length is one side of the triangle depending on what the foot position is, which will be calculated and then output to the leg based on some other maths. So at the moment the code's a bit hacky, it should be seen as code samples. I have put the code up on GitHub, but it's probably all going to get trashed, put into functions, and there's a lot more to it. So the next things to consider are the other actuator on the back of the leg. So we've only done one effectively here, which moves the knee at the moment. This is my really basic model. And of course this isn't accurate now. We've actually gone and drawn the actuator properly, so I probably need to integrate that into the CAD. At the back of the knee, there's also this other actuator that moves the thigh like this. So the original plan here was to have these two motors sort of parallel with each other, and that means that the mass is right at the top of the leg. In reality, of course, this motor isn't there, it's much further away, and I think we're probably going to have to do the same with this one in order to get clearance. So you can see in this model that when we slide this up and down, actually to get these rods clear of the motor is actually quite tricky, and that's why the motor is in that position. So the nut on the end here just clears the motor and the encoder mount there, and we are kind of limited by what belts are available as well to get the exact distance between the two pulleys. So obviously when we look at the back of the leg, if we were to have the other motor parallel, this rod will actually stick out of the back, which means that when it's basically right up in that position, it's going to be very difficult to get the rod out, because of course it would have to cut through the motor unless we put that motor in a much different position. And of course when I planned this version I made the rods really thin, these things are really thin, I didn't really consider that distance. So most of this model is now quite unrealistic. The other thing I need to work out in tandem with that is what about the actuator that actually moves the legs this way. So the other 4 motors, we're having 12 motors and 12 degrees of freedom in total. So of course we need some sort of actuator that will push that. The plan was to lay parallel actuators inside this gap, so we've got this piece of 40-40 at one end, and on the opposite leg it's that end. So the plan was to extend down this green plate and have another pivot point that pushes against this one, and then extend that green plate down and push it against that one. So we need to work out how those actuators fit. The body is actually quite narrow, but we also need to consider that when this shrinks in, and perhaps the other one does as well, that actually does leave very much space, so that's going to sort of squash the actuator, and we have to be careful that actuator doesn't bind against the insides of these legs when they rotate on the other axis. So here's our 40-40s. What we're going to have is an aluminium plate either side. We're going to have some tube that goes through to make that top of the leg pivot point, and then obviously there'll be bearings on each end which go into those green plates, and then this piece is pushed this way and that tilts the leg. So we need something that's going to push that, either go either side, or we can put a big sort of bit of studding or something through it and another rod end or something like that that's going to push it that way. So here's another ball screw. It's only a short one. It's a 200mm. The others were 250, so this is a bit shorter, and the plan was these should fit across in its belly quite nicely, driven by the motor on the end, then some sort of push rod arrangement that pushes that bit of 40-40. And what I'm going to try and use for that is 12mm smooth bar with these linear bearings, and these are sort of the linear ones that have got tiny ball bearings that go round and round in a loop inside, so those slide really well. So ideally I have the bearing mounts fixed here at one end, and as this nut travels up and down it pushes the 12mm rod, and that causes some sort of pivot point here to push that bit of 40-40, so that would sit in there or something like that, and we have another pivot point at the other end. This is getting quite wide this way now, and I've got to get these sort of next to each other, and the motor's got a mount on there as well. So I'm thinking about some other configuration, perhaps where these actually sort of go underneath here and they go closer together. And then this pushes something attached to this end, and then perhaps the pivot point goes that way, or it could go that way, and these could get turned on their sides. So here is my initial plan for that. So we've basically, as I demonstrated there, put those blocks underneath. And essentially what we've done is made this drop down piece that straddles a piece of 2020 and an aluminium bracket, and that of course pushes the actuator up and down as the ball screw slides. I don't really like this being off centre because it's going to cause this piece to twist as force is exerted through here. There's not too many other ways of doing it. So obviously the motor's all balanced on top there, but there's plenty of clearance of course because we don't have those rod ends this time. We're using these linear rods to push the force. So what's probably going to happen is it's going to be mounted this way, and then we'll have a pivot point in that end and another one somewhere at the other end, and that's basically how it extends and pushes that 40-40. Now it is possible I've moved the motor position just like that, so as it hangs, the motor actually hangs below it there, and that'll put less load on the pivot points because essentially everything is hanging below them instead of having that massive offset weight on the top. So before I try and make anything like that, we're going to try and put that actuator into the CAD here to check that it does actually fit and everything's clear, because we can. But obviously, as I said, this design's a bit out of date. So what I've actually done is moved on to the next version and put that proper motor in. So I already had the CAD from last time for the bottom half of the leg there. So I've put that in, and in fact what I've done to get clearance for those rods, as I mentioned, is actually just turn this around. So the motor's at the bottom of the leg, although actually they're both kind of in the middle anyway. There's not too much in it. It's only about 80mm lower than it would have been. I think that's pretty much the only way around it. I haven't drawn in the rods, but they would of course go from there up to here. And this is another piece of 10mm, which we need to consider because it's probably going to bend because it's quite long. Although it may be okay because we have one rod that's really close, and obviously that makes quite a rigid square. As long as the 30mm steel tube doesn't bend, we should be okay. So the next thing will be to actually mirror this, get the other leg in, and see if our new actuator fits in here, or if we need to make this slightly wider. So just stopping to consider that for a moment, it does mean that we're going to end up with another motor there, and that makes this leg quite wide. The other option, of course, is to move these motors closer together, and we'd have to move them up as well to get past this. So they could come up right, so they're sort of right next to each other here, so the leg isn't so wide this way, and obviously then it's wider this way, so that's something to consider. So for those of you who are curious, there is actually clearance, so even with this leg in this position, the motor doesn't hit this bracket at the moment, and it doesn't hit this on the way back either. And I don't think the legs will hit each other. Even with this leg right forward, there's still space for both motors, not before the feet hit each other anyway. And there we go, so I've now put those new actuators in the middle, and we can see that if we manipulate this leg, we can get 15 degrees either way for almost all of the travel, but not quite all of it, so there's still a little bit more to do, and that seems to work quite nicely. And so what I've actually done is put one motor below and one motor above. I haven't quite sorted out the mountings on those yet, they're just floating there. But from the point of view of spacing, that looks okay. And of course the other actuator moves the other leg there. And they hardly move up and down as it does that, so there's no danger of those things crashing into each other, there's plenty of clearance. Now I could have gone for the flat configuration I mentioned, but the motor's in between. The only way I think I could do that is if I moved up this green plate and moved those closer together, made the whole leg mechanism longer so they met in the middle, but I was actually planning to hang the batteries in the middle which power it, and of course I've still got to get 6 O drives on here and all the electronics, so I really need the top space clear as well. We can also see that if I do drive that into, let's just say 15 degrees, that when I manipulate this leg axis, it does in fact clear just about all the stuff there, so we're pretty much okay. It's pretty tight, and we may stick the legs slightly further out on the axles, but for now that looks like everything fits in. So I've printed my parts for this. I thought we should prototype it and see how it works. So what we've got here is an M6 here, which will attach the bearing block on there for this. Let's just pop that on. And on the back it's recessed, so I've got a countersink in there, and that means that I can put these, the linear slides, straight on there flush and bolt them on. They've already got M5 taps in, and that means everything can go together flush. So I've bolted on my 2020 and my linear slides there, so if we just pull this off, we can see the rest of the assembly. Now we need to put some pivot points on each end, and those are going to be 10mm. So one of those goes into the piece that pushes in and out, and we need to recess that into that hole so that it doesn't hit the pulley on the end of the ball screw. We also need to do the same on the other end so I can get the bearing block on. So we basically need to put that 10mm through the 2020 and recess the head into that little recess. Eventually this will be an aluminium plate, by the way, not 3D printed. So for now I just need to cut down these heads because I couldn't find any with smaller heads. And we'll have to do that with an angle grinder. Well, they're not very pretty, but they do recess in there quite well. I should probably get some other heads, although I quite like these because I've still got a cross to get a screwdriver in so I can do the nut up on the other side. So there's already a bit of strain on the bracket just here. I've had to super glue it already because the bracket actually snapped when I was testing it, and of course with the force pushing this way and the ball screw on top, that's going to put quite a lot of load around this region. So maybe we need another bracket on the bottom, tap these holes out and put something on the bottom there to hold that whole thing so it's aluminium against aluminium with aluminium brackets top and bottom. Alright, so I've got my saddle on there now, which will eventually push the rods through the linear bearings there. So I've nicked one of these off the exosuit. Eventually I'll remake those with a grub screw in. But obviously as we wind the ball screw, the saddle moves up and down. Yeah, so I think eventually I'll have another aluminium plate on the bottom that runs all the way along from the pivot point all the way underneath the linear bearings, just so we avoid that weak spot. So I've got my 12mm rods in the other pivot point, and now of course this slides really easily, so we just need to shove those into the saddle and the whole thing will be complete. So there we are, that's all fitted. I did allow holes in these for set screws to, obviously they'll be tapped when these pieces are aluminium to hold those 12mm, but the bars are really tight in here for now, so it seems to be alright. And obviously as I wind my pulley there, the thing gets longer and shorter. And we can see at this end here why the bolt head has to be recessed, and that's because this pulley has a belt round it, and otherwise it would bind on the bolt head because this thing goes right underneath it. So despite the offset nature of this, and this being pulled up here and it actually conveying force at the bottom here, this seems, you know, it seems pretty strong. I think it'll be fine once all of it's made of metal. So of course we need to mount the motor on one side, which is how I had it in the CAD there. So there are plenty of places to mount it, of course, because we've got all these bolt heads. We've got this plate here, which will be aluminium, which we can extend out to make a mount to put that motor on. Obviously the encoder we need to mount on the back again, but again we can extend out the blue plate at the other end and just make basically a simple block that sits on there that holds the encoder and the back end of the motor. So the only issue that leaves us with is how do we fix both of those pivot points to the robot. Obviously one is that 10mm that goes through this 4040, which is the actual pivot point. So that's fine, but the other end needs to go somewhere. So I've designed these brackets to be slightly differently. So we've got another piece of 4040 and another plate on the back. So of course that's the opposite on the other side. And the two without the legs attached look like these on the other end of the robot, so that leaves plenty of space for those things to rotate in their bearings, and it means we've got the other end of the pusher there. Now that does leave us with some more clearance issues, because of course we're going to find that this now sticking here means that some of our leg may run into it. So when that leg is pivoted into 15 degrees, it's that bolt again which is just sticking out, and is likely that it's going to hit this as the leg moves forward and backwards. But of course we can, as I've demonstrated, grind down the bolt heads. At the moment I'm using that lock nut on there, which isn't the best thing to do, so we could use a normal bolt head ground down. It's still possible we can move the leg out on its pivot points, 20mm or so, making the robot 40mm wider, which isn't very much on this. And that should work out nicely, so I'm pretty happy with the overall design that we've got here. The last thing of course on this design is that this is actually looking quite bulky now. We've got these two motors on here, so it's looking like it's going to have really muscly legs, which I guess isn't a bad thing. One thing mentioned in the comments from last time is we could put the motors just in line with the ball screws. There's probably enough power, and of course we'd lose that 2-to-1 ratio, but then the motors would go, or at least the ball screws would go twice as quick. It looks like there is enough power, and that will make the robot much more agile. So there's a big blank patch just here, and another one at the top of the leg where we could stick that motor in line, just couple it straight on the ball screw with an 8 to 10mm coupler. Obviously we do need to get that encoder on the back and hold the back of the motor, so it would make it quite long and it would stick out on the back of the knee there and on the top here. But there is plenty of space and there'd always be clearance because of this round here, so as the leg moved it would be fine. So that is something I could do. I think I'm going to proceed with the 2-to-1 gear ratio, but if the robot just won't move fast enough, then we will probably just go and put those in line, take the brackets off and make a new bracket. And that's kind of the beauty of making this quite modular, using this extrusion, and of course these brackets can probably just be 3D printed and won't cost very much. I'm pretty happy that can be made, and this actuator is going to be quite useful in other projects as well. It's like quite a compact little actuator. Obviously it could be longer, we could have a longer ball screw, so I'm thinking about some other ideas that could use this thing as well instead of off-the-shelf linear actuators. I'm pretty sure for the power and weight this is going to come out pretty well, and it's going to be really useful in other projects. And that's the great thing about open source. So of course I'm uploading the CAD for this today. Obviously you'll have to make sure you get the right blocks and all the alignment is correct if you're going to try and make one, but feel free to use that in other projects. And as I said before, this whole project is open source, so all the CAD will get uploaded for each episode as well as the code. and eventually I will accept contributions when I've actually built the thing and we've got a working code base and stuff like that. So there we go, and the great thing about open source is it's really inspiring other people. So Lucas sent me in a simulation of OpenDog that he made in Unity using my CAD, and you can see the animation here. So the dog's going up the hill, here it goes, and eventually it gets there and it falls over. So I'm not sure that's how it's going to look when it's walking. Obviously he's just put some joint motions in there to make it walk along, but basically this is really good that someone's been inspired to use the CAD. And hopefully this is going to be open source as well. If I've got the link to that by the time this video goes out, then I'll put that in the description below so everyone can get hold of that Unity project. I'm hoping we can actually take serial data in like I've done with other Unity projects, and we can actually drive those joints and make a bit of a simulator. I'm not sure how the physics simulation is going to work, but at least it means we could check the trigonometry and check the dog does all of the things we expect without these really high power actuators going crazy if we do something wrong. So that's really good. Alright, so as I said, the link is in the description to the CAD and code for this episode, and don't forget that all of these projects, my own projects, are supported through Patreon, so have a look at patreon.com/xrobots, and you can get access to all my videos early, sneak peeks and pictures of the next episode of OpenDog as well. I'm trying to put daily updates up about something on my Patreon wall if I can, and essentially that's how loads of these projects are supported. So thanks to all patrons, and if you'd like to support me you can, and if you don't want to, it's still open source and all the videos are free, so there we go. Alright, that's all for now.